Greetings everybody, and welcome back to our final installment on Stokes Theorem. So just as a reminder, when we're talking about Stokes Theorem, that we have three kind of pieces that are going along with that. We've got our oriented piecewise smooth surface S. We've got the boundary of S, which is going to be a simple closed curve that has a positive orientation, so that's going to be important here in a second. And then we've got our vector field that's got continuous partials on an open set containing S. Now what we're wanting to actually show in this with our example is that if we do the surface integral of the curl of f dot ds, that's going to be equal to the integral around the boundary of s of f dot dr. So the idea from the last video was that we were working through this computational example. And so just a little bit of a review. We had our vector field f being x, y, y, z, and x, z. Our surface was going to be a portion of the hemisphere. Z is equal to a squared minus x squared minus y squared. So this upper hemisphere where we've got the components of y being greater than or equal to 0. Now, what we computed last time, that we wanted our normal to our surface to be pointing up, and so for our ds, when we computed this, we had a value for the left-hand side of Stokes' theorem being negative 2a cubed over 3. So if you want to go through the details of that, that's in our previous video, video part 2. So now, here I'll give you a little bit of a warning that we're going to work it 2 times, and the first time is going to be incorrect, so that you'll see how this the importance of the boundary coming into play and it being oriented correctly, and how we figure out what orientation we need, where that actually manifests itself. And so for the first time, to kind of give you an example, we'll work it the wrong way. Okay, so warning on this one, if you're just catching this video in the beginning, this will be the wrong answer. So now for the right-hand side, we want to orient our surface so that the region that we're interested in is going to be to the left. So we're talking about our limits from the previous video. We had only positive y value, so our theta, our u value, was only going to go between 0 and pi. When we wanted the upper hemisphere, we were just having v values for going from 0 up to pi over 2. And so the region that we have was this region, and so that thing is going to be bounded by two curves, c sub 1 and c sub 2. Now, typically, kind of how we think of these, we want our curves oriented so that the surface is going to be to the left. That's what we mean by our positive orientation. Everything looks good from this. Looks like we're good to go. We haven't talked at all about how the orientation on the surface is impacted by this, and so let's see what happens. Well, if we parameterize c sub 1, then we get a curve gamma sub 1 that's just going to be pi in the first value and t in the second value, with t just going from 0 to pi over 2. And for c2, we want to parameterize that one, and going backwards with u going backwards from pi down to 0, and v being constant there at pi over 2. And so the orientation that we have for that one, just pi minus t and pi over 2 for v, so 0 less than or equal to t less than or equal to pi. Again, warning, if you're catching this in the middle of the video, this part is going to be wrong. So on our curve C1, if we take those values, we plug them into our x, y, and our z values for which we parameterized our surface. Again, check out the video part 2 if you can't remember what those are. So this gives us a vector field that looks like this. On C2, if we do the same thing, we get a vector field that has this expression to it. so that our curves, so we parameterize the curves in parameter space, and now if we kind of lift that up to the actual surface, so we plug those into our parameterization function, so gamma 1 gets stuck into our original x, y, and z values, gamma 2 does the same thing, then we get these expressions for our curve. So these are our curves that are actually living on the surface. Here's our r sub 1, here's our r sub 2. If we take dr sub 1 for that one, then we get an expression that's going to be this form. We take dr sub 2, we get an expression of this form. So that for our line integrals, if we do the integral over the boundary of f dot dr, we split that up into two separate line integrals, 1 over c sub 1, 1 over c sub 2. So over c sub 1, we've got a domain from 0 up to pi over 2. Here's our f evaluated on the curve, dotted with dr, dr on the curve. Same thing for the second one. Our vector field evaluated on the curve, dotted with dr for that curve. And so what happens if we kind of plug these, evaluate that dot product, perform the integration, then we get an a cubed over 3 for the first one plus an a cubed over 3 for the second one. So we get a value of 2a cubed over 3. And everything looks great and wonderful, right? No, it's not. From the last video, we did this integration. We got a negative 2a cubed over 3. For this one, we have 2a cubed over 3. So what on earth happened? How did we get the wrong answer out of this? Well, the thing is, we ignored orientation. And so ignoring that orientation is what really causes the problem in this case. So if that's what happened, how do we go about fixing it? Well, the idea was when we just put our curve on here, u and v, and we just aligned everything in this form, then we're really thinking when we're doing this of using a right-hand coordinate system, which means that if we just do u cross v, so the first vector cross into the direction of the second vector, then u cross v is actually coming out of the paper at us. And so what happens, we get a coordinate system for a right-hand coordinate system. We're going u cross v gives us u cross v pointing up out of the paper. But this was not the coordinate system that we actually wanted. Remember that our normal, when we computed it, we wanted the one that was facing up, and for that one we wanted partial s partial v cross partial s partial u. And so in this case, we want our first vector to be v, we want our first coordinate axis to be v, and our second coordinate axis to be u, so that when we compute v cross u, now we're getting the orientation that we want, and that's the same orientation that's kind of coming back here for our partial s partial v cross partial s partial u, so that our v cross u comes out of the paper at us. And so if we switch our u and v axes so that v is coming first, then u is coming vertically from that, our new boundary, so we still have our region here between 0 and pi over 2 and 0 and pi, we get two new curves, say C3 and C4. If we take those two curves and then do parameterization of those, this gives us for C3, u is going to be pi, v is going to be pi over 2 minus t for t going between 0 and pi over 2. C4 looks like u is going to be t, v is going to be pi over 2 for t going between 0 and pi. And so if we compare our first two sets of curves with our last two sets of curves for C1 and C3, what we see there is that u is going to be pi, first one v is going to be t, second one it's pi over 2 minus t. For the second curve, u is going to be pi minus t. For the second curve, u is just going to be t. And so what happens is just comparing those two curves, C3 is going to have the opposite orientation of C1, and C4 is going to have the opposite orientation of C2. So what then happens for our integration is that the integral over the boundary of S, when we have the proper orientation for C3 and C4, is our negatives of C1, our negative of C2, so we get a negative a cubed over 3 minus a cubed over 3, and we get the right answer of negative 2a cubed over 3. And so kind of the punchline for this, kind of the last thing to wrap this up, how do we get our orientation correct with that? Well, the orientation that we're given for the curve looks like partial x partial v cross partial x partial u. This is telling you kind of which order you to put your axes. V is going to be the horizontal axis, u is going to be the vertical axis. If we have an orientation that looks like partial s partial u cross partial s partial v, our orientation switches. And so u, the first variable, becomes the horizontal axis, the second variable becomes the vertical axis, and that guarantees that we've got the right normal coming out of the page. So that then if we orient our axes correctly, we keep our desired region, so the region for our surface and our parameter space to the left, that will guarantee that we've got the right orientation for our curve, and so that we can kind of go back and forth for however we want to compute with Stokes' theorem. So I hope this has kind of been insightful. You can work through all the details. You can find the notes for all the videos down below, and I will see you all next time.